I think we're ready to get started. So it's a great pleasure to have Vijay Balasubramanian here today to tell us about the black hole interior.
Great, thanks very much. And thanks primarily to all the organizers, Rafael and Alicia here, for example, for putting this together. It's so nice to be meeting in person again, Covenville. Thanks so much for doing this. Great, so I'm going to tell you today about the black hole interior as encoded in Hawking radiation. Now, this is based on material that I basically learned from my friends and collaborators, Arjun Kar, who's currently at UBC, Onkar Parikar, who is an assistant professor at TIFR, and Yue Li, who goes by Kathy, my grad student, who will be graduating this fall. So please keep an eye open for her applications. It's based on one paper that's out, this paper called Quantum Error Correction, the Black Hole Interior from a couple of months ago. And then there are a couple of papers in the works that, well, they'll come out when they come out on this topic. So let me start by summarizing what I believe to be, let me make sure the sizing is right on the screen. Yes, that's about right on the screen. I'd like to start by summarizing our current understanding of quantum black holes. There's been a tremendous amount of progress in the last couple of years. So where do we think things stand? So we all agree that you can start out with basically a simple cloud of gas like that. You know, it's a simple state, complicated in the statistical physics sense of having many particles, but otherwise simple. And then this collapses gravitationally. We have many pieces of evidence pointing to the idea that there is some kind of quantum chaos involved in the collapse process. Can't trace this 100% all the way to the end, but you know, we have pretty good indications from many directions. The idea is that this collapses in the end to some state that is a very complicated, in some sense, black hole microstate. And the effect of this very complicated state, when you examine it semi-classically, is that it looks like it has a horizon from behind which you can't get out. Now, the further, to me, very surprising progress of the last couple of years has had to do with the notion that then you have Hawking radiation, you know, pairs get produced, one going out, one going in, they're entangled, they're all maximally entangled pairs following Hawking. This process proceeds until after a while, you have plenty of radiation outside and you still have some interior. And after the page time, there is an assertion that the distant radiation over here includes a dual description of the remaining interior. I think this is a truly remarkable statement. And I go on, you know, on even days, I'm very happy with it. And odd days, I'm like, what the hell just happened? And I'm not sure I understand completely mechanically why this is true, even though I can do the calculations. More on that in a minute. And then there's a still in progress piece of this whole analysis as a community, where at the end, we'd like to say that this radiation proceeds. Eventually, there's no interior per se, but indeed, the radiation encodes the state of the system a long time ago, and that from this, you should be able to decode the original thing. We don't quite yet know how to do that. Now, of course, you can have many gripes about this story, starting with the fact that this is mostly said in 2D gravity, and 2 dimensions, there isn't even really a gravity. It has a negative cosmological constant, not zero or positive. And, you know, we can, there may be technical details you can complain about. You know, there's many issues that you can complain about here that we would like to sort of dot the I's and cross the T's on. But nevertheless, this is a lot of progress. This is, at least we have a picture of how things go. So today, my focus is going to be on part 4, on a piece of part 4. So I find it very, very surprising, shocking even, the statement that the radiation can contain an image, if you like, or a dual of the interior. So I'd love to know, what is the structure of the code for the local degrees of freedom in the black hole interior within the Hawking radiation? Note, this is not a statement that we're going to say something about the encoding of the microstate. It's an encoding that we're going to talk about the, you know, low-lying excitations around the microstate that are supposed to get encoded in a dual manner by the radiation. So what exactly does that mean? If that's true, shouldn't I be able to sort of wave my hands in the radiation somehow and affect the interior? Doesn't that cause problems of causality, that kind of stuff? Step 1 in that is to know, what do you do to the radiation to affect the interior exactly? It should be something very complicated. Well, exactly, quantitatively, how complicated is it? And we will try to add some, hopefully, some progress in that direction today. So the first question is how to ask this question. So, you know, we're going to look at a late time in the radiation of in the evaporation of a black hole. And there's some radiation Hilbert space gathered far away from the black hole. Then there's a black hole, and inside it and outside it, in the semi-classical description, there's some low energy Hilbert space, the code subspace as we now call it. If R, the radiation, contains B, by which I mean the low-lying Hilbert space of excitations around the black hole, then there is some operator in R that will affect B. So my goal today is just to characterize those operators in some quantitative manner. So we're going to do this to ask whether O acting on R affects B. We'll use the methods of the quantum error correction literature. So in my experience anyway, many people are not entirely familiar with how that formalism and literature works, so I'll give a brief review. I first encountered this formalism and learned it actually in a paper by Herman and Eric from 8 years ago or so. There's a nice pedagogical discussion in the book of Nielsen and Chuang that interested people can go read. But for our purposes, I'm going to set it up in the language that I'm going to use. So how does quantum error correction work, or that language work? You agree that there's a code subspace that with some basis I running from 1 through D. So there's a d-dimensional space of things, of d-dimensional Hilbert space that you seek to encode. This is going to, for us, be logically the sort of excitations around the black hole. We encode this in some physical Hilbert space. Typically, that physical Hilbert space has to be larger because you can imagine if you try to encode a large Hilbert space in a small Hilbert space, there will be some complications associated with that. So there's a larger Hilbert space. In fact, you may not be able to do that faithfully. So you need a larger physical Hilbert space. And there's an encoding map V, which for us is effectively whatever Hawking has told us, somehow produces some map into the radiation. So there's an encoding map from the code subspace into the physical Hilbert space, written as so: V acting on I produces psi I. Psi I is the physical state in the Hilbert space representing this code state. And V dagger V must be equal to 1. There are other properties you may wish to satisfy to make this a palatable code. So in the lingo used in this literature, an operation of the physical Hilbert space is a quantum channel, and it's described as follows. So let's suppose, in general, the state on the physical Hilbert space is some density matrix. It could be a pure state, but in general, it's a density matrix. We act on it with an operation E. Now, E can be broken down into a set of Krauss operators. So you conjugate rho by EM dagger with the property that the summon M of EM dagger is 1. That preserves the trace of rho. And the rank of this operation, in some sense, a measure of how complicated it is, how difficult it is to build E, is well, if M is summed, I should have said, if M is summed from, let's say 1 through L, you would say that this thing has rank L, and that's sort of a measure of the complexity of the operation, right? Not precisely, and we can debate what complexity precisely means, but at some level, this tells you how complicated it is. There's an alternative way to describe such a quantum channel that's very convenient and which we will use, which is you basically do what's called an isometric or unitary extension of this operation. So what you do is you imagine an auxiliary environment with a Hilbert space. So here's the auxiliary environment. You make up an auxiliary Hilbert space. And then you imagine that you have a unitary operator acting on the product of the physical Hilbert space and the environment, like so. You start out with the environment in the vacuum state, and U epsilon, the unitary extension of your operator, just mixes the whole damn thing up together, right? And so you can imagine, somehow it moves some of the information from possibly from your physical Hilbert space over into the environment, could do all kinds of things. So you span the environment by a bunch of states EM. The number of them is equal to the rank of the operation. It has to be at least the rank of the operation you wish to perform. And then, well, there you go. That's how you set it up. So this is called an isometric extension. Or if you want to impress people at cocktail parties, it is the Stein spring dilation. Okay. So again, in the language, action on this Hilbert space is often called an error because it's going to potentially affect the encoding that you have done. And the error can be corrected if there exists a fixed recovery channel R, such that R, the recovery operation, acting on your quantum channel, which acts upon the density matrix, gives back rho. And this must be true for any density matrix within your code Hilbert space. Now, it's important that R is fixed. You don't get to pick R depending on the state you're trying to encode. That would be a different game to play. Very roughly, what this means is that if you can, in fact, have a recovery channel of this kind, it means that the error the operation that he performed, took the entire code and kind of moved it around in the physical Hilbert space. It didn't actually do anything to the relative encoding of states. It just placed it in a different place in this bigger code, physical Hilbert space. It hasn't actually done anything. In that sense, it hasn't changed the actual states that you've encoded. So it's preserved the code. Again, there's a very nice set of pictures and discussion about this kind of thing in Nielsen and Chuang, which I do recommend. So you can ask, when is an error correctable in the sense? That is to say, there is a recovery channel, which means you haven't actually affected the code. You haven't affected the system in any way. Well, a very nice way of diagnosing that, which is going to be important for us, is as follows. It's using something called the decoupling principle. You do this, you had a physical Hilbert space to start with, into which you had embedded the code. We've already agreed, we've basically invented this auxiliary environment Hilbert space over there to represent the action of the quantum channel. We now invent another auxiliary reference space, which is a copy of the code subspace and maximally entangled, but the physical Hilbert space and the reference Hilbert space, or at least the code part of the physical Hilbert space and the reference Hilbert space. This is a theorist's sleight of hand. You shouldn't think of the reference space actually existing. This is a trick that we can use to evaluate properties of this system. So now the whole system looks like this. The whole state for the whole system is, well, you have psi I are the physical states corresponding to different code states. You maximally entangle them with the reference. You stick in here the environment in its ground state. The reference and the environment are auxiliary things I've cooked up as a theorist, and then we hit the whole thing with this unitary extension of the error, and that's the state that you get after the action of your quantum operation. Our goal, of course, is to determine whether this actually had an action on the code, changed the code, which we would interpret as saying you did something to the representation of the interior of the black hole. So if you believe the holographic duality between a part of the code subspace and, part of the radiation subspace and the interior of the black hole, you messed with the black hole interior. So how do you diagnose this? There's a thing called the decoupling principle, which states the following. So suppose you do all of this, you apply this quantum operation, and then you trace out the thing you originally started with, which is the physical Hilbert space. You are left with the two auxiliary spaces, the reference and the environment. So it says that the error is correctable, namely you didn't do anything to the interior of the black hole, to the code, if you like, if and only if the resulting density matrix on the two reference spaces, the reference space and the environment, is a product, namely it's factorized. Okay, so that's the statement. So another way of saying the same thing is right. Another way of saying the same thing is to say that the reference and the environment, after you trace out the physical Hilbert space, do not have any mutual information. So the mutual information, of course, is the entropy of the reference after tracing everything else out, plus the entropy of the environment after tracing everything out, minus the joint entropy of the density matrix on the reference union the environment. So this is very nice because once you get to things like mutual informations, we actually have techniques in physics for calculating these things. Everything else is pretty abstract. Now, the gravitational path integrals, all manner of things they can do, and I'm going to pull out every trick in the bag to calculate this stuff. That's what I'm really going to do. So in fact, I'll just mention that there is actually a stronger statement. The stronger statement says that the one norm between the best recovery channel you can write down, acting upon the error acting on the density matrix minus the original density matrix, is bounded from above by the fourth root of this mutual information. Very, very powerful statement, actually. And you can use it to show a very, very nice thing. So if you do something called an erasure error, that is to say you take some of the bits in a code and just sort of wipe them out, get rid of them, then you can show that the whole code, the whole thing will remain correctable so long as the number of bits you erase is less than or equal to 1/2 the entropy of the physical Hilbert space of the whole system minus log the dimension of the code subspace plus 1. So there's a statement like this. And one of the things I will show you later, or I will tell you later, because I won't have time to fully derive this, is that I will show how to compute this mutual information. And one of the outcomes from it is that semi-classical gravity saturates this quantum singleton bound to order 1 bits. It's basically about as optimal a code as you can possibly get in its robustness. So that's going to be one of the outcomes of today's lecture. Okay. So now I need to, Herman.
on the previous slide, at least you weren't requiring that the decoupling exactly holds. So you allow.
We're not going to require that the decoupling exactly hold.
And therefore, this is an approximate error correction,
Right.
but indeed with an error at least approximate within that
Yeah.
bound that you indicate.
Yeah. So the reason why I'm giving us some slot is at the end of the day, we're going to do some gravitational path integrals, and we'll see that some set of diagrams which dominates in one limit gives you exactly 0. But of course, you know that there's a series of terms there, all of which are giving you subleading corrections suppressing e to the minus entropy.
Correct.
And then in another limit, you'll find another term dominates, which violates this bound in a big way. And we can see that.
Right.
So I'm just, so in general, I'm going to use 0 and finite, but really we should understand everything I say with exponentially small corrections.
Correct. But so I'm missing in your inequality and exponent, since you're talking about exponentially small corrections, I'm missing in your we cover that thing in exponential. So how do I see what you're writing down that is actually an exponentially?
Is actually a what?
That is exponentially accurate. Exponentially in the diff. I would expect it an exponent somewhere on the right of your equation.
Over here?
Yeah.
The mutual information will be exponentially small.
But it's a difference. Okay, the mutual information gets exponentially small, and where can I see that happening?
Actually, I won't actually do any calculation deriving those exponentially small
Right.
pieces, but I will tell you where they all are. And I will just tell you the two limits in which it's 0 or something that's order 1, and then somewhere in the middle you'll see.
Answers my question. So basically, indeed, because of the fact that what we're talking about here are random matrices, therefore, indeed, for random Krauss operators, your condition is often satisfied indeed with exponential accuracy.
I will be very precise about this
Okay.
in a little while. I mean, I'll just calculate it from end to end. And one of the nice things about this particular setting, and well, we have to say which theory of gravity we're going to work in, is you can actually calculate every single thing precisely. And there's even an exact calculation which we haven't done involving a sum in which every term is calculable. So if you wait for half an hour,
but this still requires at least some control over the size of the code subspace.
This will be a statement that the conditions for what dominates where will depend on the following things. On the entropy of the black hole, it'll depend upon the size of the code subspace, as one might expect. It'll depend upon the size of the encoding, the physical Hilbert space of Hawking radiation. You know, how late are you in the radiation? You know, how much of it is entangled in? And finally, it'll depend, and this is the part we're really interested in, on the rank of the quantum channel. Our interest today is in how does the rank of the quantum channel required to disrupt the black hole interior depend upon these other variables that we just spoke about. There is a technical caveat that I should just chuck in, which is that strictly speaking, you know, when we talk about the code subspace and gravity, there's a piece inside the black hole, there's a piece outside the black hole. Probably worth being a little bit careful about that. So strictly speaking, when you construct the state, the auxiliary thing, there's a reference spaces for both the inside and outside part of the code subspace. So there's an inside reference and an outside reference. So the decoupling theorem that we actually want to use is that the mutual information between the part of the reference space that refers to the inside part of the code subspace decouples from the outside part of the code subspace and the environment. So that's just a technical detail which won't matter much for anything we're, well, it matters in the calculation, but it won't matter conceptually for anything we're doing. Okay? Right, that's at the code subspace level. You know, that's what we do. So the game in all of these things is to ask a question about you make the semi-classically valid assumptions, and then you do these calculations and basically ask when do they look like they're not valid, right? It's a precise conditions for that kind of thing. But at the level of the code subspace, we know, or at the level of the low energy effective field theory, there is clearly a factorized Hilbert space. If you push this to the UV, if you make the code subspace very big, for example, then you could not validly make these assumptions. Okay. So again, this is part of why there are no doubt exponential corrections to everything in sight. Right. Anyhow, the gravity model we're going to use is like like everybody, we can use this little fakey little gravity model, which is 2D JT gravity with matter. And following PSSY, we're going to cut off the other side of yon black hole by putting an end of the world brane there with a microstate on it, right? And again, you can have infinitely many doubts about this. Was that really valid? Does it descend in a nice way from a UV completed theory? And the answer is it's all unclear, but nevertheless, we're going to pursue this because many insights have been gained with that. So the action, as usual, is JT gravity. There's a brane action, and there's some field theory floating around in the back. That's going to give us our radiation, our code degrees of freedom, our low effective field theory degrees of freedom, and so on. The JT gravity, I remind you, has an S naught here, which represents the entropy of the four-dimensional black hole from which this putatively descended. Dilaton floating around, some curvatures, and there are boundary conditions that you need to place for everything in sight, which I'm not repeating because this is quote standard, as in one can find this from the literature. So of pertinence for us, the end of the brane states, there's a Hilbert space at the end of the brane states. This is supposed to be like black hole microstates. We take them to be alpha, labeled from 1 through K, and these states are supposed to have delta function overlaps. They're orthogonal up to exponentially small corrections. You definitely need those because if you take K to be larger than dictated by the black hole entropy, then these can't possibly be orthogonal completely. They will have tiny overlaps, even if they're random vectors somehow in the Hilbert space. So these things are floating around over there. Good. So this is the standard picture. And we are going to take the standard, PSSY picture of an evaporating black hole, toy model of an evaporating black hole. You suppose that the Hawking process happened, everything's maximally entangled. So you have psi alpha I. So alpha here indexes the black hole microstates. I indexes code states or low-lying effective field theory states. And then you maximally entangle the microstates of the black hole, if you like, with an external radiation reservoir. And we've pulled all the usual hokey tricks of pulling the radiation outside the gravitating part of the space. You can argue whether that's valid, not valid, etc. But that's what we're doing here. And we're going to pursue that model. Okay, so this is a snapshot of the system at some stage in the evaporation, as in all the usual models. And our goal is to increase K. Well, usually we increase K to model later stages in the evaporation. And I'll note again that the entropy of the black hole is still controlled by the parameter S naught in the action and not by K, right? Very late in the radiation, there's some complicated pattern of entanglement, but the entropy is still the entropy. It's dictated by the underlying physical system as opposed to how many quanta you happen to radiate it. Okay, the setup's done. And our goal now is to do the calculation. So we want to study quantum error correction beyond the horizon. So we will think about an old black hole that's past the page time. So that looks like just like one of these states that we've constructed. There really should be an index I here associated with all the low-lying energy eigenstates we're interested in. And we entangle it maximally with the radiation. And we take the amount of radiation, if you like, to be well past much bigger than e to the S naught, where S naught was the entropy. That's because we're past the page time, and this is supposed to be well into the radiation. So let's set it up again. The code subspace is the interior Hilbert space plus times the exterior Hilbert space in the low-lying excitations around the black hole. The encoding map is whatever Hawking did. Well, it's this. This is the encoding map, and that produces some physical state in the Hilbert space. And there it is, I've written it out. And now I've expanded this index I to be I and I prime because there's some state inside the black hole, there's some excitation outside the black hole, and there you go, that's the state. Okay.
So even after the page time, you're assuming that the Hilbert space inside and outside is.
Yeah. So in this sort of model, that's exactly what you do, because past the page time, the black hole is still very big. And when the black hole is still very big, if you are a effective field theory observer, semi-classical observer in the bulk space-time, to all intents and purposes for states that are sufficiently low in energy, we expect them to act as if they're factorized. The lack of factorization is presumed to be something that's exponentially small of order e to the minus S naught. This is something we can discuss and can debate to what degree those small effects should have added up. Was there some logical problem here? This problem is shared by, I would say, essentially all of the local, of the recent analyses. So with your permission, I'm very happy to discuss this because it bothers me too. But I would prefer to defer the discussion to the end because I'd like to show you, given this assumption, what further progress you can make. Is that okay, Gilad? Okay, but I share. I mean, again, that's another one of the classes of doubts that I have about possible logical holes in the analysis and things that need to be knocked in properly. Things make you uneasy. One of the things that makes me uneasy. Okay. So there's this complicated dance here where you make assumptions that are to be exponentially small, and some of these exponentially assumptions that have exponentially small errors. Some of these exponential small errors don't affect the outcome, and some do. And sorting that out, keeping it straight, is definitely a complicated business. So again, this is one that I would like to defer if that's okay. Going with the flow and accepting Gilad's objection as something that we do need to think about. What do you do? So suppose you want to construct one of these states and you want to describe it in the Euclidean path integral, making one of these states. What would you do? You would say the state psi I prime, inside state, outside state, microstate looks like this. Here's the Euclidean past infinity. You do some path integral, you set things up, sources to the boundary at the back, you propagate to t equals 0, you take a slice, and that's supposed to give you the state on the t equals 0 slice. Were you to wish to compute an overlap like this, your instruction would be to bracket this, complete the path integral, then you would have a slice of Euclidean ADS, end of the world brane state propagating from one side to the other side, and the low-lying excitations. Whoops, what just happened? Yeah, I and I prime propagating from one to the other, calculate, and there you go. You do the JT integral saddle integral, JT gravity path integral, and typically you do that by saddle point. So next, our concern is what happens if you apply an error channel. Well, you take the same state and you apply the error channel, so that mixes up the state with something in this auxiliary environment that we have invented. What's our goal? Here's the calculation we want to do. We wish to compute the mutual information between the interior reference Hilbert space and the exterior reference Hilbert space union environment after tracing out the physical states after the action of the error. So that is a sum of entropies, sum of two entropies minus the entropy of the union. So the trick we've learned very well over the last few years is to do these entropy calculations by the replica method. Let's recall the replica method. You wish to compute the entropy, trace rho log rho. You instead compute trace rho to the n. That's the Rényi entropy. You divide by 1 over n, 1 over 1 minus n. You take the limit as you go to 1 from above, and that computes trace rho log rho. So, all right, our job's clear. We need to compute all three of these objects. So first we need to start by computing the reduced density matrices. That's a thing to do. Then we have to compute the Rényi entropies. And then we wish to take this limit. And then surely this will depend in some way on the actual error operation. And we want to sort of dig out what that is. So that's what we're going to do. So this takes a little bit of a setup and being careful with the indices. So I'm going to write down the equations, but I'm not going to describe them in detail. I'm going to describe them a little bit conceptually, and then I'm going to draw some basically the Feynman diagrams you're supposed to compute. Herman, you look worried.
So if I understand, your I prime index labels the
part of the Hilbert space, of the code Hilbert space that's outside the horizon.
Right, so that's part of the radiation. Okay.
No, it's not part of the radiation. So I prime, so we probably shouldn't have even bothered with this.
Track of where the radiation is.
Right. So see this? When I write psi I,
yeah, so alpha R,
this is the radiation.
Yeah, but right. So I could write psi I in this way, and
so just very quickly. So really we want to put an I prime here and an I prime here. See?
Okay. Right, but where does the size of the Hilbert space enter in your whole discussion? Or the size
In all
of
the sums.
the size of the radiation. Hilbert
So,
space
so
entering
notice that
your-
here, there's a sum that goes up to K.
Right.
K, of course, measures the size or the dimension of the subspace of the radiation Hilbert space that is entangled with the interior. Not all of the radiation needs to be entangled with the interior, but some of it. So this is that part of the Hilbert space. So that's where that part is. The dimensions of the code subspace of the interior and exterior part of the of the bulk Hilbert space will appear because you have these indices I and I prime. And as you'll see, when we compute, there will be sums over these that will appear all over the place, and those will produce it.
My sharper question then is the following: is that the E operator does not depend on alpha.
E acts on the radiation and auxiliary Hilbert space, but I think you're asking,
So that's my
do you take E to have prior knowledge of what the black hole microstate? We insist that it doesn't. The story will definitely be different if you if you consider operators with knowledge of the actual black hole microstate.
I understand that part, but the question is that does E actually act on the radiation or not?
Yes, it only acts on the radiation, and we are going to write that in terms of the radiation auxiliary environment, but only acts on the radiation, does not act on the bulk Hilbert spaces.
But this is my quantum channel. It's not my recovery operation.
It's just the quantum channel.
Why would it act on the radiation?
Because that's what I want to do. The question I would like to understand, at least for the purpose of this talk, is you tell me that this radiation contains an image of the interior.
Right.
What do I have to do to the radiation? That's an operation of the radiation to interfere with the interior.
No, but that's not the question. What you have to do to the radiation is not the quantum channel, it's the recovery operation.
No, what I'm going to do is I'm going to act on the radiation with my quantum channel, and I wish to ask the question whether what I did was recoverable, which means I didn't do anything, or not. So, but the action of my bomb that I tried to put off is the quantum channel. I then separately want to ask the question whether this action could be recovered.
Then my question is your bomb a physical thing or not?
Whether it's a typical thing or not.
A physical thing or not?
Okay, so this is, so I think of it as a physical thing, right? It's a physical operation I perform on the radiation. I'm doing it. And that produces something in the interior. That's the language we'd like to use. So this has to do with whether or not this is an abstract code which you're manipulating in some way, or whether you're physically acting on it. I want to think of it for the purpose of this talk as a physical action on the radiation. It's a unitary, it's an operator that I'm acting on that plus the environment.
Yeah, I don't understand the logic because then later on you're going to introduce a recovery operation that's going to undo your quantum channel.
No, only if it's recoverable.
I understand, but then.
Yeah. So what would that mean? That would mean the following, right? That would mean you took the radiation, and my physical operation of the radiation rotated the whole thing. Let's say that is a physical action on the radiation. I rotate the entire Hilbert space. Right. It can be recovered. There's an inverse rotation that will bring it back. It's also the case that that operation will have the character that it doesn't actually do anything to the part of the to the interior Hilbert space of the black hole.
But basically, what you're doing with your EMs, you're scrambling actually your radiation Hilbert space already in combination with the interior of the black hole. So E acts both on the exterior of the black hole and on the radiation.
Well, that's only because of the assertion that the radiation, because of its entanglement properties, whatever, is dual to the interior. I mean, that's the assertion we're making these days. We're making the assertion that there's a piece of the radiation Hilbert space that's actually dual to the interior, right?
Yeah,
I mean,
mathematically, I don't necessarily disagree with you, but physically, I would say, let me just give you what my picture would be on the same story.
Yeah.
My picture on the same story would be is that your E's are actually the full time evolution from your number one in your slide, your initial cloud, to your final entangled state. That is what E is supposed to represent.
That's a different problem.
But
We could definitely study that
It-
too,
it
but
has
that's
the-
not
it
what
has
we're
the
studying.
same- It has the same mathematical expression. And in that case, I would actually have an explanation of why why it's acting on the radiation. Because basically the full evaporation process
Yeah,
is a linear map.
right.
Will
So-
produce some radiation state.
So,
And then I have a physical definition of what the
Yeah.
EMs
So-
is, and then my recovery operation is the thing you would have to do.
so we can definitely, so I'd be happy to talk about that. And I think you
Right.
can present this in that language,
Right.
but that's definitely not what we're trying to do, right? What we're trying to do here is we're trying to say that there is this state in the system, and I wish to perform an operation on it that messes with the structure of the encoded space. And I would like to ask, what characteristic does the operation have to make that happen? So if if E was simply the unitary transformation going from, whatever the initial state is to the final state, well, it just unitarily encodes the input into the output. There's not a question of whether it's recoverable or not.
But then the manipulation you're going to do is the recovery operation.
So it might help if I walked forward a bit more, and then in about 4 slides, can we have the same discussion again? Yeah.
So just wanted to clarify. So the quantum information problem is the following. You have you have an old black hole that radiation encodes the interior, and you want to study how robust this encoding is.
That's a fine way of putting it. Yes. Yeah. Herman offers a different interpretation of what's being discussed, and we should definitely talk about that, but in 4 slides after I actually set up the calculation. Okay. So at the moment, at least at the technical level, our goal is to, what did I just do? Our goal is to calculate these, the various Renyies. So when you do these, each state, is some, psi, I prime, etc. What's going to happen? You get to multiply all of these bras and cats. Each row, there's some path integral that constructs each of these things. You multiply them all out together. You take some traces. Well, it's clear what you would do to compute trace row to the n, right? You bra cat, multiply n times, and you take a trace. So if you take this thing, this is, for example, the Renyi entropy associated with the interior part of the bulk Hilbert space, you get a bunch of things that look like gravitational overlaps. More on that in a minute. If you take the other 2 Renyies, one which looks like the Renyi associated with the exterior and the environment, and the other one, the whole thing, you will get similar gravitational overlaps with sort of different index structures. They'll do what they do. Times an object, which I'm going to call the F tensor. And the F tensor is an object that is purely a function of the quantum channel. Here, it's important that you assume that the operation you perform doesn't know what the black hole microstate is. So you can't sort of put in sort of gravity stuff directly in there. So you have to do something like this. Sort of messy expressions. And it's actually slightly easier to visualize this diagrammatically. So I'll just draw the diagrams that you're actually trying to compute. So first, let's talk about the F tensor, an interesting object. So it has indices that correspond to the environment, indices that correspond either to the radiation of the black hole microstate, depending on which way you want to think about it. And then you have unitary operators and the conjugates that sort of act on those things. And then you have lower indices and upper indices, and you can draw it in this way. So each of these involves a unitary operator taking 2 incoming states and rotating it in some way. Our goal is to contract this tensor with the gravitational overlaps. And the way that looks is you take sort of this object with all of these pieces in it, you take the dangling edges, and you got to contract it. When you contract it, well, what you've done is you've contracted it with the result of a gravitational path integral. So in that gravitational path integral, these are the boundaries associated with that gravitational path integral. And various indices like the these end of the world brane indices or microstate indices have to contract into those gravitational path integrals. This is going to be the structure of the thing. So then you have the gravitational path integral part of it, which basically means you have these boundaries, and you're instructed to do a path integral to fill this thing in. Now, how should you fill this thing in? In the old days, we would have said that just look at whatever overlaps you have here and compute those path integrals separately and just write it down. That's what you would have supposed to do. But in the old days, if you were Simon, you would have said, as he has actually said to me before, that you should sum over all possible topologies. Why? Because it's gravity. You tell me the boundary conditions, you should just sum over everything. So for example, if you want to do the third Renyi, here are disconnected topologies, the thing we were done in the old days, so to speak. So here's one gravitational, here's one boundary, the end of the world brane, finishing it up. You have here the two indices associated with the bulk excitations, the contractions that I was describing earlier, go around like this, and there's some indices here contracted with the F tensor. Little complicated to look at, but also beautiful to look at, and certainly doable as a calculation. If you pick a different Renyi, then you'll get a different pattern of contraction of these indices, right? So it just goes on like this. You got to do a bunch of contractions of this kind. So here I've drawn the 3 disconnected saddle points with for the third Renyi in these cases. So that means you had 3 overlaps, gravitational overlaps, and you evaluate each one separately. For the same third Renyi, there are also connected topologies. Here's the maximally connected one of them, where you have this boundary, and this boundary. The end of the world brane index, you connect between these universes instead of connecting it within the universe. You allow the sort of particle indices to sort of flow between the universes, and here are the 3 replica copies, if you like, and you connect the whole thing here. So this is basically standard Euclidean gravitational path integralology. I've done nothing in some sense really in any way novel. That's just a diagram that exists if you allow topology changing amplitudes in Euclidean gravity. How do you evaluate this? You can do all the standard, there's a replica symmetry here. You can use Lefkowitz Maldacena to evaluate this conveniently and so on. I'd also like to mention that in addition to these maximally connected geometries, there are many partially connected topologies that also contribute to the sum. And I'll say a little bit more about those later. They're interesting. Anyhow, at the end of the day, this is a calculation. And you can evaluate the disconnected diagrams. And you find, for example, this Renyi entropy is the dimension of the interior code space to the power 1 minus n. N is the Renyi index. The dimension of the exterior code subspace raised to the power 1 minus n times the trace of this tensor, sigma n, n to the n. I'll tell you what that is. And there's 3 terms of this kind. So the sigma n is an object that only depends upon the quantum channel. So what you do is you take, if you like, the maximally mixed state on the radiation, that's what this is. You tensor it with the ground state on this environment that you extended with. And then you act with your channel on this, and you trace out the radiation. So that object is what I'm going to call sigma n. And as you can imagine, what we want to do is to evaluate this object for specific classes of interesting channels in a minute. Right? We'll do that. For the moment, just accept this, because already, without evaluating particular errors, good stuff is about to happen. So likewise, you can now compute the Renyi mutual information, plug everything in, and you will discover that the disconnected diagrams produce no mutual information between the reference and the environment, and therefore there's no way, if that was the only part of the gravitational path integral that contributed, that you could do anything at all to the radiation, possibly up to e to the minus s corrections, right? There's nothing you could do to interfere with the interior. Now you can repeat this analysis with the maximally connected diagrams, more work. And this time there's a different tensor that appears here. Once again, you take the maximally mixed state of the radiation times the ground state in the environment, you act with the error, and this time you trace out the environment. So this is a tensor that's on the radiation, not the environment. And again, it only depends upon the quantum channel. It's a characterization of the quantum channel. And now you calculate the same mutual information. You get 2 log di, where di is the dimension of the interior code subspace. So when the connected diagrams dominate, you see that the error will affect the interior in this sense. So our goal is, of course, to determine which errors cause the connected diagram to dominate. Before we do that, for specific errors, there's actually a general characterization you can give. If you ask, when do the connected diagrams dominate, you basically need to take the ratios of these terms, right? And see when 1 is bigger than 1 or less than 1, etc. So you can take the ratios and then go from the Renyi to the von Neumann limit by taking the n goes to 1 plus limit. And you find that the characterization that you have is, remember, we gave 2 characterizations of the structure of this quantum channel. You act with the quantum channel, and you either trace out the auxiliary environment, to get sigma r, or you trace out the environment. You trace out the environment to get sigma r, or you trace out the radiation to get a tensor environment. You compute their entropies. This is the von Neumann entropies here. You take the difference, and the condition that you affect the interior with the action is that this is less than the black hole entropy, well, less than minus the black hole entropy minus log the interior code subspace dimension. This is an object known in quantum information theory called coherent information. So you see, there is a crisp one-line characterization of what it takes to affect the interior in these pictures by acting on the radiation. The interior is affected if the channel has a sufficiently negative coherent information. Jonathan. Actually, let me see. I'm 15 minutes short. Well, let me just take the question and then.
Oh, okay. I'm wondering, in the standard PSSY model, there's
In the standard, what cases what?
the original West Coast Replica wormholes paper. There's a very important interplay between the size of K and the size of e to the s naught, and their relative size tells you whether you have an island or not. And it hasn't seemed to me like that's showed up here at all, and I'm a little concerned or confused by that.
Yeah.
Do you have any comment?
Yes, I do. So I've, in extracting leading terms and sticking them down everywhere, I've assumed this is a black hole that's been radiating for a long time with K bigger than e to the s. Strictly speaking, the other terms floating around, but it would be more complicated right now. So absolutely, we've made the assumption that K is large enough. If it's too small, the calculation is not interesting. You're going to get zeros everywhere. Ahmed?
I don't have a question. I just want to see your previous slide more carefully.
What's that?
I just want to see the previous slide more carefully. You went too fast there. Thanks.
Okay. So now we can get this is all very, very crisp. So we can get our fingers into this and actually calculate these things for different class of errors. We did it for two kinds of things, random errors and for erasure errors, both with super interesting results and a nice calculation. I only have time to describe one, so I'll describe the random errors, and then I'll tell you the outcome for erasure errors. So for random errors, what do we mean by random errors? We're going to suppose that the unitary extension of our quantum channel is unitary operator U epsilon, acting on, of course, a product of the radiation Hilbert space and the environment Hilbert space. So then what's the dimension of the product Hilbert space? It's K times L, where K here is supposed to be, it's not really the full radiation Hilbert space I'm interested in. I'm interested in the part of the radiation Hilbert space that's entangled with interiors. That has dimension K, and the environment has a dimension L. Well, L is at least as big as the rank of the channel I'm acting with. So we're going to take it to be as small as possible, and L is the rank of the channel I'm acting with. That's the minimal size I need in order to be able to represent the operator in this way. Now, I'm going to take U epsilon to be a Haar random unitary. So in other words, I don't know what to do to affect the interior. I'm going to pick a random action and just act and see what happens. So remember, so I'm just going to tell you the calculation schematic. It's a very pretty calculation. So schematically, we want to calculate things that look like trace rho to the n, rho being some density matrix. Schematically, those things look like gravitational overlaps times these F tensors. So I'd like to know, on average, if you hit this thing with a sort of random gigantic operation, on average, what does it do? Which means I want to take the average of this, of trace rho to the n. So that average is going to pass through the gravitational overlaps and just act upon the F tensor. So we can focus on that. So because of course the average means average over UKL, unitary group of dimension KL in the Haar measure. So what does that look like? Schematically, again, this looks like that average is an integral over the unitary group with lots of sums and m's and gammas and what have you of u daggers times u's, just sort of this sort of messy looking object. Fortunately, unitary group is probably the best studied group on Earth, and these are standard integrals. You can read these answers off from the math literature. There's the Weingarten expansion. It's a very beautiful piece of algebra, really, all of how to do these integrals. And there isn't time to tell you about the details of this. I really enjoy this particular part of the computation. What you get is a series of terms, right? So depending upon, one way of thinking about this, you've got U's and U daggers, and they've got upper indices and lower indices. It's like doing tough double line diagrams. Indices will contract with each other in different ways. You can pick different contraction patterns, and that'll produce suppressions by powers, and you can just and then integrate. And so you get a series of different sort of index structures. So I'm going to tell you about 2 of them in principle. So you compute this average, and there's a long series of terms. There's one term with this index structure. Remember, alpha and the alphas and betas here are either indices. You can think about this as indices on the radiation Hilbert space, or as indices of black hole microstates, because they're entangled together. So you're running over the same indices. So you get this index structure, delta alpha 1, beta 1, alpha 2, beta 2, etc. And there's a minus sign missing. So let me just put the minus sign in. Whoops, that's unfortunate. There we go. So you get this thing, and then you get a second term suppressed by k to the 1 minus n. Remember, k is the dimension of the radiation Hilbert space, L is the rank of the operator that we're acting with. And there's a different index structure, alpha 1, beta 2, alpha 2, beta 3, etc. Now, well, if you look at this, the blue terms dominate when L, the rank of the error, is much less than k, which is the dimension of the Hilbert space. There's additional terms here that involve L's and K's that are left out. That's why I have to put that condition. It also turns out that this index structure precisely matches the index structure of the disconnected diagrams. So there's a precise match, okay? And so when you multiply these things into all possible gravitational path integral diagrams, it'll turn out that this index structure matches, so it's like a template match between this and the index structure coming out from the disconnected diagrams. So anybody who's done Tufte double line kind of diagrams, right? You have these terms and these terms. If the index structures match up perfectly, every loop counts, and you get more powers. And you break the index loops because you reconnect them in some funny way. You suppress it in powers, right? So what this is going to do is it's going to pick out this piece of the integral for the average, this piece of the average of a random errors is going to pick out the disconnected diagrams in the gravitational path integral. Conversely, these green things have a different index structure. They dominate when the rank of the error is very large. In fact, this is the most important term, when the rank of the error is very large. It matches the index structure of the maximally connected diagrams and is the dominant, and that has that as the dominant contraction. If you take this index structure, you contract with all the gravitational diagrams, it's like it's like a filter picking out the maximally connected diagram. It's like in some real sense. So in fact, there's a systematic correspondence between the possible tensor structures of the Haar averaged F tensor in our language for a random error, and the tensor structures arising from the gravitational path integrals with n boundaries of different topologies. It feels like there should be something deep there, as in different topologies for a quantum channel on n copies of the radiation density matrix, and different topologies for the gravitational path integral are somehow in correspondence, but I don't have anything deeper to say about that. We're almost at the end. All right, so you calculate. So you remember there were these blue pieces that extracted disconnected gravitational diagrams. They give you 0 for this mutual information. So whenever those pieces dominate, you can't affect the interior. If your error, if your operation was somehow dominated by these pieces of the F tensor, you couldn't affect the interior. Whereas if the green piece is dominated, you get 2 log di, and you could affect the interior by that error. That's the idea. So when does this dominate over this? You can do a little bit of a calculation, and you'll find it's when the rank of the error greatly exceeds the dimension of the radiation Hilbert space divided by the dimension of the code subspace, multiplied by the exponential of the black hole entropy. And this is a number that's much, much bigger than the dimension of the radiation Hilbert space. There you go. That's the answer. So you learn to affect the interior, the channel U epsilon must have a rank that's exponentially large. And a thing that would be really nice to do is to sum up this full series. I think it can be done because everything is so beautiful and arranges itself so well, but we haven't summed it up. So I'm ready to finish. May I just summarize? I'd like to finish. We started 5 minutes late. I'd like to finish before the 5 minutes is up and then take the question, if that's
Take
okay.
your time.
So So let me summarize everything I told you. So we described this sort of gravitational path integral way of evaluating mutual informations that tell you if the action of a quantum channel on the radiation in this model can affect the black hole interior. We showed that if the disconnected geometries dominate, then that the relevant mutual information vanishes and the quantum channel does not affect the interior. If the connected geometries dominate, it does affect the interior. We gave a criterion involving this coherent information. That's a characterization purely of the quantum channel. You don't need to know anything about gravity to evaluate this thing. The only gravity comes in here, where this enormous number, that's the black hole entropy that you have to, that's involved there. And so if this coherent information is sufficiently negative, then it's the case that that's an operation that's supposed to affect the interior. I told you one more thing, that for random errors, the result was the connected phase dominates, and therefore you get this very, you can affect the interior if the rank of the error is sufficiently big. The one thing I didn't get to tell you about is what I'm going to summarize now as a result. So another kind of error, if you want, when you're playing with this kind of thing, is an erasure error. An erasure error is a really, really severe thing to do. You take a bit in your system and you erase it, you get rid of it, right? Crazy thing to do. So, and earlier on, we said that on very general quantum information theory grounds, there is there's this thing called the quantum singleton bound that characterizes how many erasures a code can tolerate before something gets messed up, right? So we're imagining the erasure is a thing you're doing to the radiation, and we're going to see if it does something to the black hole interior. So the explicit evaluation from above, and this is also a very nice calculation with a different diagrammatic expansion, shows that the gravitational radiation code is robust to T erasures, with T as the black hole entropy minus log base 2 of the dimension of the interior Hilbert space divided by 2 plus some number of order 1. So this is precisely this part, the quantum singleton bound, exactly it. So here there are sort of order 1 corrections when you look at the calculation, but it's possible that if you add in the corrections beyond these leading saddle points that we use, the connected and the maximally disconnected, maybe it would remove this. So there is some sense in which, at least in this model, the radiation is a maximally robust code. It gets absolutely to the limit of what you can achieve. It's trying to protect the interior, if you like, from you messing with it as best as it possibly can. I'm going to stop there. And Ahmed.
Regarding your analysis of the Haar random errors, did you calculate so you calculate the average in the Haar ensemble, but did you calculate the fluctuation?
We calculate the average in the Haar ensemble.
Yes.
The fluctuations is something we're thinking about. That's a very interesting thing to do.
Yeah, because this is not conclusive by itself. You need to look at the fluctuations.
Yeah. So there are indications that the okay. So this is the average, and so we did this in 2 ways. So we have some calculation of the fluctuation. I can tell you about that offline separately. That's an interesting thing to do in its own right, as you well know. The other thing you can do is, by the way, you can take this coherent information. So look, so here what I did is I took these expressions that involve gravitational path integrals, these F tensors, and just averaged a lot and stuff like this. The other thing you could do is I already have a criterion, this coherent information criterion. That's as a separate thing. So it's not obvious that averaging the coherent information criterion gives you the same thing, will give you the same result, because it's averages under logs and under sums and things like this. But it turns out it does. So that's a separate calculation that gives the same answer. That too potentially has fluctuations that you could look at, but I don't have enough to say about that today.
It might be that this quantity is just positive, and so the fluctuation it's have to be small.
I can't remember what we made some arguments about this that I can't actually remember. We had some argument as to why the fluctuations were small, but I'm actually not recalling them right now. Is really what's going on, and we have some calculation somewhere about it.
Thanks a lot, Vijay. Very interesting. 2 quick questions. Some of the stuff went by a little quickly for me. The erasure channel, it acts on the radiation system, which has dimension k. So its rank is upper bounded then by k squared. Is that correct?
It's what?
Upper bounded by k
What
squared.
is upper bounded?
The rank of the channel is upper bounded by k squared then, correct?
Because we have k bits to erase.
Yeah.
Okay.
Basically. Right. So the comparison then, when you're looking at L is much bigger than k, the maximum that could possibly be is k squared is much bigger than k, and I guess this is okay because we're taking k to be parametrically large.
Yeah.
Okay. My second.
But notice that this thing was derived for random errors, not for erasure errors.
No, but even for a random error, the rank of a quantum channel in a Hilbert space at dimension d is
Yeah.
maximally d squared.
Yeah. Well, you can always make L bigger, but it's useless.
Well, if you make L bigger, then your Krauss representation is bad. It's redundant. You should have just used fewer Krauss operators.
Sure. Okay.
Right. Okay. Second question. This erasure equation that you've written here, I don't know very much about these things, so maybe you know, or someone else here does. Do you know if this is quantitatively different from the claim that Jeff and Patrick made that black holes saturate the alpha bits bound?
I don't know. Saturate the what?
The alpha bits bound?
So I wish I knew what the alpha bits bound was.
Okay.
So the answer is I can't tell you if it's the same thing.
Okay. Maybe we can talk offline.
Let's talk about it afterwards.
I'd like to understand better how your calculations sort of, well, whether they commute or not with, let's say, the page curve calculation, where you don't worry about losing any part of the radiation or errors happening with the radiation. You're just asking what you can recover from the radiation you caught. So for example, in the last case where you were about erasure, it seems to me that that could be regarded as a special case of just the ordinary page curve calculation, because if you lose part of the radiation, why isn't that just the same thing as being at an earlier time where it hasn't come out yet? I mean, it doesn't matter very much which part of the radiation you lose. It just matters if you have more than half of it, but by
Okay, so perhaps that's related, but I don't think of the page curve calculation as thinking of actions on the radiation that do something. But you're completely right that if you just sequester some of the radiation and don't look at it, then that's a little bit like saying that you move those bits over into the environment of this language, and thus you kind of erase them.
You assume the black hole acts as a scrambler, and then you just compute using the gravitational path integral the actual entropy of an appropriate amount of the total radiation. You can think of it as just giving you the total radiation, you only get to look at part of it. Whether more came out and you lost some of it doesn't really matter.
Yeah.
That's what you have access to.
So I can't swear 100% of these two things being isomorphic, as in being the same calculation, but it sure sounds to me like that is very similar to, or maybe the same thing as looking at erasures, but I can't swear to it. It's not the same thing as a random error, of course, but that's a different thing. That involves, scrambling the thing in some other way and asking, when have you changed whatever it was? When have you acted on the interior in some way?
But in that case, you always have to assume that you know what the scrambling unitary is to have a chance, right?
No, you make up a scrambling unitary.
On part or all of the radiation?
This is acting on all of the radiation. So you could also do it in part of the radiation. This is basic, or if you pick a random unitary, randomly, you might pick something that acts only in part of the radiation. That could happen. This is an average over all of these things. Part of the reason why Ahmed is emphasizing, making sure about the fluctuations is important is because you need to be careful. You know what? I believe these things are actually, I think these things, by the way, are positive, and so there won't be zero. So actually, positive is positive here, and zero is actually zero here. Yeah. It's an interesting idea to think about looking at just the early radiation or an intermediate part of the radiation as being like an erasure channel, and then asking which part of the island do you keep or not keep and things like that. That's an interesting idea. But okay, yeah.
We're set. Okay, let's thank Vijay again.